end of today, and then I want to remind you that the first exam is not this Friday, but the Friday after that. All right. Do you guys have any questions?
I don't know if you've mentioned it already, but what's the format of the exam going to be like?
It's going to be take home, and I think about 3 questions.
Like qual
3 questions
level
for an hour. Yeah.
Okay.
Yeah.
Thank you.
All right. All right. So I guess I'll just get started. So okay. So we're gonna do more module basic stuff, and then we're hoping the goal. So the goal that we have is to do this fundamental theorem of modules over PIDs. I am having an internet problem. Let me see. Let's see. Huh. Is the app loading for you guys?
Yeah, not for me.
Not for you?
Yeah, not for me either.
Okay. So let's see what we'll have to do. So maybe I need to switch apps here. Paper. Let's do okay, great. Oh, this is empty. So I think I have to add pages now. Okay, so I'm just gonna write in here, and then I'll post this in after the talk today. Okay, so let's see if this is the right size. We want this one. I think that's the one we want. Okay, so we're gonna do more module basics. So again, the goal is to do the fundamental theorem. So the goal. So get to modules over PIDs. Fundamental theorem of modules over PIDs. Okay. And one thing that I said was I talked about direct sums a little bit last time. So let me just say a little bit more about direct sums. Okay. And so there was a criteria that there was. So there was a criteria. So there's a criteria for showing a module is a direct sum. So M. So let M be an R module. This is totally general. And you could even take this as a definition if you want. But let M be an R module. And let N1 and N2 be submodules of M. Okay, so M is isomorphic to the direct sum of N1 and N2. If and only if 2 conditions, you have to check 2 conditions to check that something's in direct sum. The first condition is that M is equal to N1 plus N2, right? And the second condition, so this is equal to the set of, N1 plus N2, where N1 is in N1, and N2 is an N2. And then the second condition you need to check is that N1 intersect N2 is the 0 submodule. Okay, so you can either take this as a definition or check this. So let's say that the proof of this is an exercise. Okay, or take it as the definition. For me, the definition is that these are just tuples of n1 and n, and then you add them, you add them tuple wise, and then the scalar multiplication distributes. So the R multiplication distributes. Okay, so
would that be the direct limit or the?
So this is actually the other definition is that you can take it as a colimit. It's a colimit of the diagram with two dots, where these two dots go to N1 and N2. So like you could define, okay, so if you really want to define it correctly, then you have a functor here, and you have N1 and N2. So in particular, you have kind of like two arrows. And all I'm saying is that this is a category where, you just have two objects, and they only have the identity morphism on themselves. And then D of N1, or D of the first dot is N1, and D of the second dot is N2. And then you take the colimit of this diagram, which means you take the cocones, and you take the initial object of the category of cocones. And this is what, and then you can check that this is the same thing, right? That the thing that I was talking about with the tuples is what you get. Okay, if we wanted to be completely from the ground up categorically, that's one way to define it. Most commutative algebra books don't go that way, but I mean it's totally valid to do it this way. And that's, I guess, the more modern way of doing it. The downside of that is that you just have more to check. But I mean, it's the correct definition. Okay. And it allows you to use all the theorems for, I mean, I'm going to use this fact freely. So I guess an exercise would be to check that this is the colimit. And I guess you should do that at least one time in your life to check that that this is the colimit, that this direct sum thing is the colimit. Okay.
So I ask a question just about this direct sum and being isomorphic to M. What does that map look like?
This map here? Yeah, so I wanted to give you an example, right? So here, so it depends on what you have. So right now it's just an abstract isomorphism, and I wanted to give you an example of how this is used, right? So that's why I brought this up, because I wanted to show you how this criteria is used in practice. Okay, so let me give you an example application, which is something that we use quite frequently. That's a good question. Okay. Okay. So let M. Okay. So let this be a surjection. Be a surjective map. Of R modules. Okay. If there exists something that splits this map, so let me tell you what that means. So if there exists some J from J from N to M, such that let's say M such that okay, now I'm going to write the composition in kind of a funny way. I don't want to write the composition symbol every time. So I'm just going to write them like I'm multiplying them together. And this is the identity on N. Then M is isomorphic to the kernel of F, direct sum the image of J. Okay, so this is something that we can prove. And I'm going to prove it using the criteria that we had before. Okay? So let's do this. So first, let's do the proof. Okay, so let me just say something else too. So first, observe that since J has a left inverse, the map is injective. J is injective. Right? If it didn't have it, so the idea here is that it can't be injective if you kind of collapse two elements, right? So you can't, if you collapse two elements, then you can't have a left inverse. All right. Okay. So this means we can identify n with J of n, its image in n. These two things are really the same. I mean, we won't really use this, but I just wanted to tell you that when you have an injective map, right, you can view the image as kind of isomorphic to itself. Not kind of, it is isomorphic to the source. Okay, so to prove the result, right, so to prove our claim,
This is kind of a generalization of the rank nullity from linear algebra in a way, or?
Yeah, I mean, yeah, it is. It's just saying that, yeah, it's saying that there's nothing in the kernel. So anytime the kernel is 0, then it's just totally general. I mean, I don't know if there's a category like this, but yeah, if the kernel is trivial, then you know, the thing that you map it to, the image is isomorphic to the source. The kernel measures how much the image is not the source, really. Right? So it's something about trivial kernel. Okay, to prove our claim, we will show two things. And what are the two things we will show? And this should become like super, super routine to you when you're starting to show things are in direct sum, right? The two things that you need to show are that the kernel of F, intersect the image of n is 0, and 2, that the kernel of F plus J of n is equal to 0. Or sorry, is equal to the whole thing. Is equal to m. Okay? So we need to show those two things, and when we show those two things, that's proving that the two things are in direct sum. Okay. So let's first show the claim, right? So all right. So now let's show that. So let's show that the J of n intersect the kernel of F is 0. I called the map F, right? Oh.
Yeah, you did.
How do I go back? Here. Okay. Okay. So what we'll do is we let M be in J of n intersection the kernel of F. Okay, this means that M is equal to Jn for some n in n, right? Okay, but it's also in the kernel. So this tells us that F of M is F of J of n. Okay, this thing is 0 since m is in the kernel of F. And this thing is equal to the identity on n, because that was what we supposed, right? That this thing was the identity, and this is just n. Okay, so this proves that that n is equal to 0, and hence Jn is equal to m is equal to 0. So we showed that the element was 0 by taking it in the intersection. Okay, so that's the first part. Okay, let's show the second part. That Jn plus the kernel of f is equal to all of m. Okay, and the trick here is to so the trick here is okay. So we'll write, let m be in m, and then we'll do this. M minus, and then we kind of like project it and lift it back up. Jf of m plus Jf of m. Right? So we have two pieces here. This is equal to m. Okay? I claim that this one is in the kernel, and then this one's in the image. The fact that this is in the image of J, this part's trivial. Agreed? It's J of something, so it's in J of n. All that we need to show is that this thing is in the kernel here. Okay, so let's do m minus J f of m. Let's apply f to this. Okay, so this is f of m minus, and now we have f j f of m, right? But jf, right, is really the identity. This is the identity on n composed with f of m. So we're really like doing this. Okay, and so this is f of m minus f of m, which is 0. Okay, so this proves that m minus jf of m is in the kernel. And we're done. Okay, so your question was, what is, so this gives you an example of how to show two things are in direct sum. To show two things are in direct sum, you check that it's 0 and then you check that it's m. Or you check that the intersection is trivial and that they span the whole thing. Your question was, what is this isomorphism here? The map here is that you take m and you'll map it to, in this case, it was m minus jf of m. And then this was jf of m. Right? This is the isomorphism in this particular case.
And so this map is kind of dependent on context. In this case, it was this one. And
Yeah.
we kind of like through showing that these were in direct sum, kind of led us to this.
Yeah, exactly. I mean, that's what to prove something's in direct sum, you'll get something like this. You'll get some map, right? But to show, we can't write down what the map looks like in general. We can give it a name, but it doesn't really tell us anything, qualitative about the map.
Okay.
Yeah.
Yeah, I guess. Yeah, my question was, is there a general form? And so, yeah. Okay.
I mean, you can always have a projection, right? So, the general form of the map. This is cheating, right? So you always have f. So if m is, if you have an isomorphism to A direct sum B, right? Then this thing always has two projection maps. So this has the projection onto the B part, and this has the projection onto the A part, A and B. And the projection on the A part of AB is A, and the projection on the B part of AB is B, right? And so you could say that, so you do have something like this, that f, well, f of x, or let's say f of m, you could say that this is f, the projection of A, of f of m, projection of b of f of m. But that doesn't tell you much, right? So
Mhm.
that's not so useful.
Yeah.
But it's true. But the thing is
Yeah.
that both sides use f. So yeah. Okay. So that's all I really wanted to say about direct sums. Maybe let me say a couple more things. So we want to get into this. Maybe we'll get into this later. So this has to do with splitting of exact sequences, what I wrote down. But let's not bother with this quite yet. Okay. All right. So let's do the isomorphism theorems. Let me just state them for you guys so that you have them. And the proof is going to be an exercise. So, all right. So let's do the isomorphism theorems. And maybe it's a good exercise right now for you guys to try and think about what the isomorphism theorems are going to be. So what were the isomorphism theorems for groups? What were they for for ideals, rings and ideals? And we have, this is maybe your third time you've seen isomorphism theorems, probably more. Okay, so let's do the theorem. Okay, so one is that if phi from m to n is a morphism of R modules, then we have the following, that phi of m is isomorphic to m modulo the kernel of phi. Okay. The second thing that we have is that if we have two containments, m mod n1 and 2, then we have the following. So m mod n1 of n2 mod n1. So this is isomorphic to m mod n2. Okay. So it's like you can cancel. Okay. So there's an isomorphism of posets. Of partially ordered sets. So this is okay. So here we need to fix for m n an R module and an R submodule. Okay, so it's that submodules of the quotient are in bijection with submodules of M containing N. And so if I took some submodule A here, A bar, so this looks like some submodule of M mod N, then this thing maps to Q inverse of A here, where Q is the map from M to M mod N. Okay, and the same thing, the map goes the other way too, is that you could take something here, A, the map the other way goes, A goes to A mod N. So this is the bijection. So this one goes here, this one goes here. Okay, then we have one more. So let me let me pause for a second since you guys don't have a copy of this. Okay, so this is the canonical quotient map. I think I said that. So the last one is this one that you rarely use. think I use this one the least. So if let's say n1 and n2 are submodules of M, then n1, then we have this formula. n1 plus n2 mod n2 is isomorphic to n1 mod n1 intersect n2. I think I tried to give you exercises where you use all of these at least once. Yeah, hopefully I did. All right. Okay, so the proof will be in exercise. So yeah. All right. So let's see. So I think I have to do no Therianity. So no Therianity is going to be the same thing as pretty much. It's very similar to no Therianity for rings. So let me just say, let me do no Therianity real quick. Okay, so definition. Okay, so the ascending chain. So let M be an R module. We say M satisfies the ascending chain condition okay, if what? Well, every ascending chain of modules terminates. If every ascending chain of R submodules terminates. So this means that if you have M1, it's contained in M2, contained in so on, right? Then there exists some T such that for all S, let's say S1 and S2 greater than or equal to T, we have M of S1 is equal to M of S2. Okay, so all these chains, you can't have an infinite collection of submodules which are proper inclusions. Okay, so let's define what it means for a ring to be.
Can you go back briefly?
Yeah.
Thank you.
Taylor,
Yeah.
I might have asked this when we talked about no Therianity for rings in general, and maybe this is a rather naive question, but M is an R module. Wouldn't that make all of these ascending chains terminate at M?
No, because you could keep going, right? So it could be like that they're so the example is like if you have Z, okay. So if you take Z of, let me do this in another color.
I think part of that question would be like M itself is not in the chain that he wrote down necessarily also. So.
Yeah, M is not going to appear as a finite. Yeah, exactly. If M appears at a finite letter, right, then it's trivial. I agree.
Okay.
Right?
But it
so
need not.
Going to have a finite chain, right? But the thing is that you wanted things that are proper submodules. So like the common example, the non-Noetherian example is like you take Z of x1, x2 in infinitely many variables, So let's just not stop. I was going to stop, but we don't want to stop. Okay. So we have this, right? This is R. And then in this case, we'll let M equal to R as well. And then you take I1. This is X1. This is contained in I2. This is X1, X2. This is contained in I3. This is equal to X1, X2, X3. And then you just keep going, right? And then if you do it like this, these are all R submodules of this R module. It just so happens that this is this R module M is also R itself, right? But this is an infinite chain, and this proves that this is not Noetherian, or does not satisfy. Well, I got ahead of myself. Let me just say what Noetherian means. It's a Noetherian if it's, so let me give you so let me give you the theorem, okay, about Noetherianity.
Cool.
Okay. So the theorem. Okay, so let M be an R module. Okay, the following are equivalent. Okay, and now before I do this, okay, any of these conditions that I write down is going to be the definition of Noetherian. They're all equivalent, so you can take any one of them to be Noetherian. Let's see. Did I say? No. I guess I have to give one the definition. Okay. So let's give let's do it this way. So what I still said is true. So in our module, M is Noetherian if it satisfies the ascending chain condition. It's kind of maybe not the cleanest way to do this, but okay. Or I could have written the chain condition as number 1 here. It doesn't matter. Okay, so the following are equivalent. M is Noetherian. So that's the chain condition thing. So I could have written the chain condition here instead of defining Noetherian being the chain condition. Okay. 2, every non-empty set of submodules has a maximal element. And then 3, that every submodule is finitely generated. Okay, the proof is pretty much exactly the same as in the ring case for ideals. So the proof is very similar to the proof for ideals. Ring setting. Okay, where you need the axiom of choice. All right, I believe, right, you needed the axiom of choice to show, I think number 2. I forget which implication had the axiom of choice. Do you guys remember?
Yeah, it should be the having a maximal element.
Yeah, having a maximal element, because then we used, because then you use chains, right? So then you use chains, and then you show that it was bounded, and then that's where you apply Zorn's lemma, I think, right? So, okay. So so some books will, so depending on the book you use, So either use the ascending chain condition, this condition number 2, or the number 3. 1 and 3 are by far the most commonly used as as the definition, but you need 2 to relate 1 and 3. That's kind of the important point. And then we don't really use, so in practice, I don't think we use 2 as frequently. Okay. Any questions on this? Okay. So let's do annihilators. So torsion and annihilators. Okay, so definition. I said this at the end of class last time, but let me just repeat, or 2 times ago. So an element M and M, so M is an R module here, is torsion if and only if there exists some R in R such that Rm is 0. Okay. So all right, and so given, so we can take all the things that annihilate, and so we say that R annihilates M in this case. Okay, so we say R annihilates M. That's the verbiage we use. Okay. So now let's give another definition. So so given M in this R module, the annihilator of M is, yeah.
I was just looking at Dumb and Foot real quick. Is it, they say is called a torsion element. Is it sometimes just you almost are using it like a verb?
Yeah. Is a torsion element.
Okay. I've never seen it used almost like a verb like that. That's kind of cool. I'm just curious.
Yeah. So is a torsion element is the same thing as being, so you'll say it's torsion casually, I guess. Is a torsion element is the same thing. Okay. So the annihilator is the set of all R and R such that Rm is equal to 0. Okay. So here's some exercises. And you should be able to do this in your head. So 1, and maybe we'll just talk about it real quick. 1, this thing is an ideal in R. Okay. 2, so torsion. So tor M or M tors. So 2 different notations for the same thing. So is an R submodule of M. Okay, so these 2 things. Here's what we have here. Okay, so this is the collection of all torsion elements. This thing here. Okay, and I should say this should be non-zero. Okay.
Okay. I was going to be, one of my questions was, does 0 count as?
Yeah, it should be non-zero. It should be non-zero. I actually, I think we don't need it to be a non-zero divisor, but I'm going to check this after class. I'm 99% sure this is so that you just need it to be not zero, not just a non-zero divisor. But I want to check that just in case. But let's take this to be the definition right now. Let's talk about this number one real quick though. This one's easy to see. Okay, so here. All right. So how do we see this? So like you just need to take two things that kill it, and if one thing kills it, right, you just need to do that. That's also going to kill it, right? And then you need to do that. Is that going to kill it, right? So if R1 kills it, right, then R1 kills it and R2 kills it, then R1 minus R2 is going to kill it. And if R1 kills it, then really R times R1 is also going to kill M, because of associativity of scalar multiplication.
Mm-hmm.
Okay? All right. So that's why this one's kind of really quick. All right.
Wait, how is torsion different than zero divisors again?
Because it's a module, right? So it is
Okay.
zero divisors in the, it is the zero divisor. So yeah, if R is equal to M, if R is equal to M, then M torsion is the zero divisors.
Okay.
That's
Right?
kinda
But
cool.
the thing is that you could have like R, you could have some weird, you know, you could have some weird R module, you know. Yeah. You could have something, yeah, a little bit stranger. I'm trying to think of it. So like, yeah. Like an abelian variety, like, or an abelian group, right? An abelian group doesn't necessarily have an entire torsion part. So like in this fundamental theorem of modules over PIDs, right? We're going to have the torsion part, and then we're going to have the non-torsion part, right? And you know, that doesn't really correspond to zero divisors because there's no multiplication in a general module. Okay, so definition. So a module M is called torsion if M is M torsion. Okay, so examples. You know, Z M is equal to Z mod NZ as a Z module. M is equal to Q mod Z as a Z module. You know, in general, you could do M is equal to K times, or K mod R as an R module, where R is a domain and K is the fraction field of R.
Can you briefly say again what the fraction field is?
Yeah. So the fraction field of R. So this is the set of A over B, where A and B are in R, and B is not equal to 0. Right? And the addition and multiplication is, you know, A1 over B1, A2 over B2 is A1 B2 plus A2 B1, B1 B2, and multiplication A2 B2 is equal to A1, A2, B1, B2. Okay, so so this is what the fraction field is. Maybe I should say one more thing about the fraction field here, is that to test when two elements are equal, you have to subtract them and check that they're 0. So this is equal to A2, B2, if and only if and only if A1, B2 minus B2, A1 is equal to 0. Okay, so you just kind of like separate the numerator. So sometimes this thing is formally defined, the fraction field, as ordered pairs with this addition and multiplication relation and this equivalence relation. So this defines an equivalence relation. So let me write that down. Formally, this defines an equivalence relation on ordered pairs. You know, AB. And then this thing is, so you take all the equivalence classes under this equivalence relation, right? And then you define an addition and multiplication like so.
Okay.
So this is an example. This is one example of what's called localization, which we'll get to pretty soon. Example of localization.
And as kind of a follow-up, so we're only able to define a fraction field when we have a domain because of this.
Right now, yes. In the future, no.
Okay.
In the future, we'll be able to define all sorts of fractions, and that's kind of like, okay. So that's kind of a really important point, is that there's kind of like, okay, there's two operations that are really important in ring theory. One is taking quotients. The other is localization, and they're kind of equally important, right? And they're sort of dual to each other. And yeah, and so there's a whole theory of adding fractions to a ring, right? And yeah, and that's it. It turns out to be a super important operation. I guess that's all I want to say about this for now.
Okay. Yeah. All right.
Okay. So let me do one last thing. Okay, so let me do one last thing. So we talked about cyclic R modules. Okay, so recall that a module is cyclic an R module M is cyclic. If M is isomorphic to Rm, right? For some M, or let's just say not isomorphic to, equal to. For some M and M. Okay, so here's what I wanted to say is that, so here's a lemma that's not difficult, is that Rm is isomorphic to R modulo the annihilator here. So you can check this. Okay. Okay, so let me do the quiz, and then maybe we'll do this at the beginning of next time. Okay, so the quiz problem. Okay, so prove that z adjoin the square root of 5 is not a UFD. Okay, so so take 30 minutes. Do it without a book. No, closed book. Just say closed book. Don't talk to each other about it. Just do it, right? And then send me the answer. Send me your proof. Okay, and then I will give you feedback. I am going to stick around for a little bit in case you guys have questions. Yeah, so I'm going to turn off the recording now, and I'm going to post this document.